All right. Okay. So thanks for coming this talk, and we already 10 minutes past almost. But so the next 30, 40 minutes of time, we are going to talk about writing hypervisors, so developing hypervisors and using hypervisors for security research on Windows. And so this is the takeaway of this talk in a very nutshell. So basically, developing a simple hypervisor is now easier than ever for you. Because I wrote HyperPlatform, which is Windows-centric open source hypervisor project. And although HyperPlatform is for security research and simple hypervisor, you can do many interesting things by using your own hypervisor-based tools. However, one thing to be aware of is that if you try to write hypervisor for your own product or with product quality hypervisors, it is going to be challenging. So if you plan to do integrate hypervisor into a product somehow, plan ahead and make a buffer if you are creating some project plans or something like this. So that is basically what I am going to tell in this talk. By the way, this slide will be shared on my Twitter account after finishing my talk. And so this is the outline of this talk. So first we're gonna introduce ourselves, and then let me explain why you may want to write hypervisors. I'm always surprised when I give a talk about hypervisor. Actually, a lot more people are coming to the talk. I expect how many of us are interested in hypervisors? Maybe 5, 10? But actually, there are definitely more than 10 people. So I'm always surprised how many of you are interested in writing hypervisors. And then we're going to explain what HyperPlatform is and what you can do with the project. And then I am going to cover a couple of the most important technical aspects of virtualization technology, EPT and VTX in general. And then Timo is going to explain challenges in writing high quality hypervisors or integrating hypervisors into products. So let me begin with myself. So I am Satoshi, and a creator of HyperPlatform. And I've been a reverse engineer for years and have strong background, reasonable background in malware analysis. So especially I'm interested in rootkit analysis. And just recently joined a CrowdStrike.
Yeah, my name is Timo Kreuzer. I'm a software engineer working for CrowdStrike, and before that I have been a contributor to the Reactors project for a long time, and I've been working on the bootloader, the OS kernel, HAL, Win32k, and different other parts. So I have a lot of background in OS internals, especially on Windows.
Thanks. Yeah, so let me start with a reason why you may want to write hypervisor or want to research hypervisor technologies. So I'm going to explain a couple of classes and 2 reasons to research hypervisors. The first one is mostly to understand technical aspect. It can do by using virtualization technology, you can do many interesting things, and you can implement, for example, additional security. By using virtualization technology, you can implement memory space isolation or protection techniques, or you can monitor access to sensitive system resources. And good example of using those techniques is virtualization-based security introduced with Windows 10. So as this illust shows, the virtualization-based security is strongly relying on hypervisor technology. And by isolating memory, it protects lsass.exe from the pass-the-hash attack, or internal component, HyperGuard, named HyperGuard, which protects like sensitive system resources from being modified by like unauthorized processes or drivers. So you can implement that kind of security, additional security, by using virtualization technology. And the other reason you may want to develop hypervisor is for reverse engineering. So as I said, I have a background in malware analysis and particularly interested in rootkit analysis. But if you try to like reverse engineer rootkit, you will realize that there are not many options in terms of tools or technologies. So how many of you have used process monitor? Yeah, awesome. Yeah, so it's pretty essential tool, but it doesn't work very well for rootkit, like kernel mode malicious code. And if the tool doesn't work, maybe you could implement similar tool by yourself. Like probably some of you may know like technique named like inline patching, like code modification, like API hook technology. So with that, basically that technology is like updating assembly code at runtime to execute your own instrumentation code. So the below picture, so this is the original code. And if you apply that inline hooking technique, like it can change like this, you can change like this, and then execute your own instrumentation code. It works very well in user mode, but in kernel, it doesn't work because there is a patch guard. So if you modify like kernel mode code, then the patch guard detects that modification and issues a bug check. So this technique cannot be applied. But if you use hypervisor, then you can do something interesting. Like because you can like isolate memory space, well, maybe you can implement invisible API hook. I indeed developed a prototype project after developing HyperPlatform. So basically, you install, like you modify assembly code, and it is executed, but it's not readable. So patch guard cannot detect, and then just you can run your instrumentation code. And you can also, like because you can like monitor sensitive system resource access, you can directly use that feature to get more like information about the activity of malware code. So sounds like the problem is already solved. We can just use hypervisor, like virtualization technology. But of course, it's not that easy. Probably some of you may know if you have tried. So there are many challenges into writing hypervisors for Windows security research. So I classified like all problems into 4 categories. So let me explain like those categories, like problems, one by one. So the first problem is in flexibility. So if you try to write your own hypervisor, you will probably start looking for existing lightweight hypervisors. And then you will realize that those existing hypervisors are designed for specific purposes. So it is not quite easy to extend or modify for your own purposes. You're writing hypervisor for security research, for example. And the other one, a simple visor, which is very recently written. And this is purely designed for education. So because it is designed and written for education, it's a great resource for learning. But if you want to do something more practical in terms of like security research, if you want to do something meaningful, you will have to write a lot of code, including hypervisor code, which is not definitely trivial. So those projects are not quite good starting point for security research. And the other problem is compatibility. So some of those existing projects do not support modern platforms. So some of them do not support even 64-bit architecture, which is now pretty essential. So this is quite significant limitation. And we don't want to start with like those code base probably. And the other challenge is simplicity. So like existing Windows-centric hypervisors and option, then probably we can start with existing like mature hypervisors like VirtualBox or QEMU for them. But as you might know, those projects are quite big and can be complex to extend or deploy. So you will be discouraged if you try to update those projects for your own purpose. If you are paid, probably okay. But if you want to do like spare time or not super dedicated for the project, you probably don't want to start with those projects. And I found that Box was kind of an exception. So it's actually like relatively easy to understand and extend the code. But the Box is, as you know, it's not fast. So it kind of limits your usage of hypervisor. It's not also a good base to start programming your own hypervisor or virtual machine monitor. So as an answer to those challenges, I developed HyperPlatform. So this slide basically summarizes advantages of HyperPlatform. So for simplicity, HyperPlatform can be developed and debugged by Visual Studio and WinDebug, so just like standard software drivers. And it supports all modern Windows systems. And this is designed for as a platform from the first place, so it's relatively easy to extend the code. And according to some benchmark software, its performance overhead is around 10%. So it's totally usable and I would say efficient. And so let me explain how HyperPlatform can be used, or you're going to use HyperPlatform. So HyperPlatform is just a software driver. It is just a kernel mode driver file. So this is loaded into a kernel like ordinary software driver files. But once it is loaded into kernel, it activates the VMX mode of the processor. And once the VMX mode is enabled and system executes or does some certain actions such as modification of control registers or occurrence of exceptions, or when someone tries to execute certain instructions like CPU ID, the processor triggers an event called VMExit and starts executing the VMExit handler, so basically event handler. And that handler is implemented inside HyperPlatform. And how you are going to use HyperPlatform is like this. You are going to add your own code on the top of HyperPlatform to do something what you want to do. Maybe just logging, or maybe adding some security feature. So you will be adding your own additional logic on the top of HyperPlatform. So let me demonstrate example of such logic. For example, what kind of logic you can add on the top of HyperPlatform. So in this demo, I am going to add a logic to detect modification of control register for SMEP flag. So it's an example application for additional security. So this control register for SMEP bit is a register that controls a processor security feature, and it should not be modified by random drivers. But there is a driver, a vulnerable driver named Capcom.sys in the wild, and that guy has a feature to modify, to disable that SMEP flag. So I am going to run those install this driver and run this exploit and show successful exploitation first. So basically this driver disables security feature and the exploit deploys shellcode into user mode but executes that shellcode with a kernel privilege. Then spawns system privilege command prompt. Then we are going to add HyperPlatform on that system to detect that exploitation. Flashed for some reason. Alright, so I am going to demonstrate in this virtual machine. So now let's install the vulnerable driver first. So installing the vulnerable driver into the system and then running the exploit. So this exploit disabled security feature, like disabled SMEP flag, and then spawned system privilege command prompt by using that vulnerable feature. And next time I am going to install our HyperPlatform with extended logic to detect that exploitation, well modification of control register 4. So HyperPlatform is, as I said, you can compile HyperPlatform with Visual Studio and debug it with WinDebug. And now what I'm going to do is adding code to instruct the processor to trigger PMExit when this SMEP bit is modified. The one. And then also adding additional code that reacts against modification of SMEP flag. So basically just issuing, basically it's issuing bug check. So stopping the system to protect an exploited system from being from being executed for further exploitation. So basically just stopping the system instead of letting exploit run. and compile this project. Oops. And now we got the compiled file and copy it into the virtual machine and install the HyperPlatform. And then if we execute the exploit, HyperPlatform should detect modification of control register 4 as we added such logic. So it triggered a bug check because it detected exploitation. So HyperPlatform detected exploitation and issued a bug check to stop the system. And the other interesting technical aspect of virtualization technology is extended page tables. So extended page tables is basically one more address translation layer. So this chart illustrates how the address translation takes place. So basically, address translation is like converting virtual address, which we are using in programming, and converting that virtual address into a physical address to fetch a memory content from physical memory. So in standard system without EPT, so we get linear address, virtual address as input, and then processor consults a data structure named page tables to get information to translate that virtual address into a physical address, and then fetch a memory content from physical address, physical memory, by using that physical address. And once EPT is enabled, the processor uses that physical address as input as well, and then consults the other data structure named EPT page tables, which is introduced with virtualization technology, and then do similar translation and get the final physical address to get actual physical address. The nice thing about the extended page tables is that you can set additional permission to the page. So you can configure whether the page is writable or readable or executable. So this chart illustrates how that extended page table is used. If some code tries to write, say, page X, then processor looks for extended page tables to tell whether that page is writable or not. And if it is writable, then the processor just executes the instruction. But if that page is configured to be read-only, non-writable, then processor triggers the VM exit. And HyperPlatform can do something interesting, what you want to do. So let me demonstrate what kind of things you can do with this technique. So in this demo, I am going to show very simple memory protection based on virtualization technology. So I am going to set a memory region named HAL dispatch table to be non-writable. So basically protecting that region. So this HAL dispatch table is an array of function pointers, and it's often modified by traditional kernel local privilege exploit programs. and we will be set this page as non-writable, and then get VM exit and detect this modification as bad activity. So this below chart illustrates how we are going to demonstrate this idea. So basically, there is a vulnerable driver named NSG64, and exploit program exploits the vulnerability, and the driver modifies hard dispatch table. But because we are setting that page as non-writable, we get VM exit. And then we can do something meaningful, like protecting the system, or in this demo, we will just roll back the change. So program tries to change, and then we restore the change to disable that modification. Okay. So first, I'm going to demonstrate unsuccessful exploitation. So first, loading the vulnerable driver, and then running the exploit. Oops, sorry. Running the exploit. So this exploit modified hard dispatch table to execute its own shellcode, and then launched this one, like system privilege command shell, by executing that shellcode with kernel privilege. But the next time, I am going to install our hypervisor, which protects hard dispatch table from being modified. By the way, those demonstration programs are all available on GitHub, so you can check it out later. So installing virtual hyperplatform-based hypervisor tool, I would say. So probably it's better to see. So this hypervisor has set protection on hard dispatch table, so it's now non-writable. And if we run the same exploit, which modifies this hard dispatch table, sorry, I didn't install the driver file as well. And if we run the exploit, so it couldn't spawn system privilege command prompt. So what happened is, so this exploit has modified the table. We tried to modify, but our hypervisor has detected the modification. So here, so detected modification, and then rolled back the change. So as a final result, the hard dispatch table hasn't been modified, and because the exploit couldn't execute its shellcode in kernel privilege, actually didn't execute the shellcode, just spawned normal command prompt. So you can implement this kind of memory protection by using virtualization technology. So one more interesting usage of EPT, like example usage for security research, is like monitoring the execution of non-pager pool. So non-pager pool is a memory, so in heap in user mode. So this is just a memory. So the left side of this chart is an imaginary kernel address space. Some space are backed by image file, which is driver files, and some pages are backed by just memory. So it's not backed by any files, driver files. And we are going to configure the EPT page tables to let execute image address spaces. Because those are image driver files, it's totally fine to execute. But non-pager pool, this is just a heap. So if someone just tried to execute heap, well, non-pager pool in kernel, it might be suspicious, and we might want to like investigate who tried to execute and what code is executed. So we are going to set this non-pager pool to be non-executable by using EPT. And I think we are running out of time, so I'm going to skip the demo, but I can demonstrate in person if you're interested in. So basically the concept is that, so if someone, in this case malware, rootkit tries to execute like non-pager pool, and this robust rootkit actually deploys unpacked code into non-pager pool, which is configured to be non-executable at this time. And this rootkit tries to execute this unpacked code backed by non-pager pool. And then processor consults the EPT page tables, and because this is non-executable, it triggers dmexec. And then we are going to log who executed or tried to execute the non-pager pool. And then we are going to change EPT page tables to make it executable temporarily. And then let the processor to try again. And this time, because non-pager pool is now executable, just that code can execute that non-pager pool. Then as the final result, what we could do is we are able to monitor, like log, execution of that non-pager pool. And if we can log, maybe we can then attach the system and extract that non-pager pool to get some interesting code. In this demo, it's going to be unpacked rootkit driver code. And for further learning resources, there are some good hypervisor projects. As I said, HyperVisor is a good project as a starting point. It is written for education, so it nicely illustrates some can be like complicated concept, like complicated virtualization related concept, and how to program hypervisor in like concise code. So you can probably start with HyperVisor if you are not familiar with concept of virtualization technology in terms of how to program it. And then also there are some other interesting projects, like if you are interested in like multi-platform support, or if you are interested in how to implement nested virtualization, like those projects can be interesting. Those are a little bit more complicated and large, so probably not as good as like HyperVisor to take a look at first, but it definitely a good resources. So that's a good side of story. So I just told you guys like writing the hypervisor is awesome. It's simple and you can do many interesting things. But there is a other side of like writing hypervisors. Can you explain like the other side of reality?
Yeah, I'm going to answer this question. Can I use that in my product? Many people might want to put a hypervisor in their security product and ship that to their customers. But the answer to that question is not so fast. There is a number of challenges that you need to be aware of if you want to put a hypervisor in your security product. At CrowdStrike we had a hypervisor research project which I've been working on the recent month. It is a custom implementation, but it was inspired by both SimpleVisor as well as HyperPlatform, and it adds a number of features on top of the hypervisor itself, features that Satoshi already mentioned. The issue number one that has to be considered when having a hypervisor in a product that ships to customers is that the hypervisor needs to communicate with the OS or with software running on the OS. The problem here is the exit handler does not run in a proper operating system context. It could, for example, run while holding a spin lock, and that basically means you cannot use any Windows kernel function from the hypervisor's exit handler itself. So that means to communicate to write communication between the hypervisor exit handler and the operating system or other software, you need to use an interrupt service routine and inject a vectored event. A vectored event is basically an interrupt that is inserted or injected by the hypervisor's exit handler before continuing to run the guest code. So when execution continues, after the exit handler is done, it will trigger an interrupt, and that interrupt will cause the interrupt service routine to be executed, and that one can then do appropriate handling, for example, WPP tracing or whatever you want to do there. This has, this means the driver itself has to be a plug-and-play driver. This is because to register an interrupt service routine, you need a physical device object, which you can only get when having a plug-and-play driver. It does not have to be a full plug-and-play driver with an in-file. There are other possibilities. Alex Ionescu did some talk about that. He basically invented a mechanism that allows to dynamically load a driver as a plug-and-play driver and then dynamically unload it without writing any in-files. The question is, what happens when interrupts are disabled? When your exit handler runs and interrupts are disabled on that CPU, then it is not possible to inject a vectored event. Or when you try to do that, this will cause a failure, and you cannot continue. So there is a solution to that, and that is called interrupt window exiting. This is a feature that when you're in the exit handler, you enable that feature, and the next time the interrupts get re-enabled in the guest, it will automatically trigger an exit. So the next time interrupts are on, the exit handler will be notified, so you can then inject the interrupt after interrupts are enabled on the guest. An alternative solution is to use posted events. Posted events work with the epic, the interrupt controller. It requires to enable a virtualized epic. I'm not going into details here. It is more complex, but it's an alternative, and I just wanted to mention that. There is one feature you have to also take care of, which is interrupt steering. Interrupt steering means that the interrupt service routine does not necessarily run on the processor that where the interrupt was injected on. So you might inject an interrupt on CPU 2, and the interrupt service routine actually runs on CPU 0. So issue number 2 I'm going to talk about is using the features. And as an example, preventing a malicious driver from disabling SMAP, that's pretty simple. You just have to check a bit in CR4, and when somebody tries to disable this feature in CR4, you will get an exit, and the exit handler can prevent that. That's pretty simple. But when it comes to other features like using EPTs to prevent either patching or execution of memory regions, it gets a little bit more complicated. First of all, with EPTs you can set individual pages to being either read-only if you don't want them to be patched, or to non-executable if you don't want them to be executed. This obviously requires an analysis of the virtual address space, because you need to know at which regions are executable or writable and which are not. This is OS version dependent, so different OS versions, different Windows versions have different kernel address space layouts. There is kernel mode ASLR. For drivers, you can enumerate the installed drivers on the system, but there is no unload callback, so you don't get notified when a driver gets unloaded. So this is all not trivial and requires a lot of complex code to handle that. Obviously, this works very well or basically the EPT mechanism works well if you have non-paged memory, because you know, once you have enumerated the address space, you know where that page is. But as soon as you have paged memory, then this virtual address might get paged out and be moved to a different location, and EPTs work on the level of physical addresses, so you need to also handle that. So an option would be to make pages, for example, if you want to prevent execution, you make the pages either executable but then read-only, or you make them writable but then not executable. So whenever an executable page gets paged out and reused for something else, it will be written to, and it will be then trigger a VM exit, and the exit handler can then take the appropriate action to either allow the modification or not. And once this page gets executed, then again, if it was a writable page, then it can, the exit handler will have to decide whether this is an executable page and set the EPT appropriately. Okay.
So, problem solved? Well, maybe not, because there is another issue, issue number 3, PatchGuard. PatchGuard is present on all x64 versions of Windows, and it's only active when the system boots without a kernel debugger. So some people never experience PatchGuard running because they always have the kernel debugger attached to the system, and once they run without the kernel debugger, things happen. PatchGuard is highly obfuscated code. It is self-decrypting code, so it actually can write to the same page on which it currently executes. It runs either as a DPC, which gets run like every 10 minutes or something, or it can be in a worker thread, so it can run on different RQLs. And the pages on which it runs are random pages. They can be from one-page pool or from system PTEs, so it is really hard to detect where these pages are. And they are different pages every time PatchGuard runs. So the self-decryption mechanism requires read, write, and executable access. Otherwise, you will get an exit on every instruction that executes, and that will cause so much overhead that the system will bug check. The problem is that obviously conflicts with the option to either make them read-only and executable, or make them read-writable but non-executable. So, to fix that issue, you need a mechanism to identify PatchGuard pages and make them read, write, and executable, but only those pages. You also need to make sure to clean up these pages, because otherwise, you leak read, writable, and executable pages, and since those will never again trigger a VM exit, you cannot automatically clean them up, so you have to provide your own cleanup routines for that. And the question always remains, do we catch all PatchGuard pages? What if PatchGuard gets changed in the next Windows version, adds a new feature, and are we potentially introducing a security leak by allowing other pages to a malicious driver to pretend to be PatchGuard? So this is not trivial. Issue number 4 is Hyper-V. Obviously, customers might want to use it. So, for example, Credential Guard, Device Guard, and HyperGuard. These are security features that you don't want to force the customer to disable. It's present by default. It's just a simple checkbox. So the question is, can we get below Hyper-V? So having Hyper-V run on top of our own hypervisor. Well, Hyper-V is initialized early as a UEFI boot service. So it will require to have an own UEFI boot module to load the hypervisor in there before Hyper-V actually runs. This also means it will require to implement full support for nested virtualization in the hypervisor, which adds another level of complexity to the code. And it requires that basically full operating system boot must be possible on that hypervisor. Issue number 5 is performance. So you might want to know how expensive are the VM exits. On a Haswell CPU, it's about 500 cycles. As a comparison, a system call is about 100 cycles. So you want to make sure that you do not have a huge number of exits. Keep them at a low rate if possible. On VMware, when using nested virtualization, an exit can be as expensive as 7,000 cycles or even more. So you probably don't want to have that, on a production system. The impact of EPT is also interesting. It is very dependent on the workload. Some workloads show barely any impact, others show a higher impact. An average value can be 20%. And the overall impact of the hypervisor is feature dependent, obviously, if you use EPTs or not, or what kind of configuration is deployed to the hypervisor. And it can be below 1% if you don't have EPTs enabled and if you don't use many features, or it can be 50% and higher depending on what you are doing with it. Issue number 6, operating system and application compatibility. I'm going to mention one specific aspect here. A hypervisor can introduce timing issues, things that normally on real hardware just execute within a few cycles can introduce through a VM exit. Okay, we're running out of time. So we're going to provide the slides. I'm going to finish here. So basically, just finish this. There is a detailed analysis for timekeeping in virtual machines by VMware, if somebody is interested. So I hope that brought some light upon the issues that come with putting a hypervisor in a production software. Thank you.
We are going to be in conference today and probably tomorrow morning. So if you have any questions, please find us and give me any questions. And those slides will be shared online on my Twitter account. And so that's it. Thank you for coming.
Thank you, Satoshi. Thank you, Timo.